Have you ever wondered how geckos can stick to walls? Their feet are covered with thousands of tiny microhairs called setae that help to increase the contact area between their foot and the surface. Where an unstructured surface might be unable to penetrate the microscopic surface asperities, the setae can deform to fill these irregularities. And when they make close contact with the surface, the charges of the atoms interact, causing attraction by means of van der Waals forces. Now let's take a look at a simplified model of this contact so that we can understand the origins of this adhesive force. We'll start by looking at what happens when an elastic sphere makes contact with an elastic half-space. We know from our experience and our engineering intuition that both the ball and the surface will deform a certain amount, depending on the amount of force applied. If we ignore the effect of adhesion, you may recognize that this is the phenomenon known as Hertzian contact, which we studied in depth earlier this semester, and found that we could relate variables of load, contact radius, indentation depth, and contact pressure using only the ball's radius and the Young's modulus and Poisson's ratio of the two materials. The derivation of these values is a little involved, but you end up with these equations. But to apply Hertzian contact, we must make several critical assumptions. First of all, we assume conformal contact. In other words, at the first moment of contact, the contact shape is one-dimensional, either a line or a point. Second, we assume small deformations. This means that the radius of contact, A, is small compared to the radius of the sphere, R, and ensures that we remain within the elastic region for both materials. Third, we assume that no friction or adhesion occurs at the contact interface. But if we want to find the force between the seta and the surface, we need to incorporate the effects of adhesion. These intermolecular forces give rise to an adhesive force at the interface and can even change the shape of our contact. In the rest of this video, we will examine what happens when we don't assume a frictionless or adhesionless surface. But first, we need to talk about something called surface energy. Surface energy is the energy required to disrupt the molecular bonds of a material and create a new surface. Every material has an associated surface energy that impacts its adhesion to itself and other materials. Materials with a high surface energy, like silicon, adhere easily to other materials, while materials with a low surface energy, like Teflon, are more non-stick. You can usually tell if a surface is high energy or low energy by the shape a drop of water forms. If the surface is high energy, it attracts the water molecules and the water spreads out. But if it's low energy, the surface tension of the water dominates and the water balls up. Unfortunately, these surface energies don't perfectly predict the adhesion between two surfaces, because we also have to consider the interactions between the specific surfaces given by their interfacial energy. Using this, we can calculate the work of adhesion, or the energy required to separate two materials to form two surfaces. You'll notice that for two identical materials, this is equal to twice the surface energy. This value is important to understanding the interaction between two bodies when adhesion is involved. Now that we know how the materials can affect the adhesion of two surfaces, let's take a look at what role the shape of contact plays. In a 1971 paper, scientists Johnson, Kendall, and Roberts developed a modified version of Hertzian contact mechanics that incorporated adhesive interactions only within the contact area by balancing the stored elastic energy with the loss in surface energy from the contact. They also assumed spherical contact, a large radius of curvature, and small elastic deformations. Here are the equations that they found. With this model, they made several interesting observations. First, the intuitive. The adhesive interactions increase the depth and contact radius of the contact. We also see a neck at the edges of the contact shape that looks almost like a solid meniscus. Finally, the non-intuitive. Because of the spherical shape of the contact, the elastic properties cancel out and do not affect the tensile load sustained before separation, also known as pull-off force. This means a stiff surface and a compliant surface will be just as sticky provided that they have the same surface energy.
In fact, this force varies linearly with only two variables, work of adhesion and sphere radius, making it simple for us to calculate the adhesion in such a non-conformal contact. You'll notice that in the pressure equation, we have the same term we found in the Hertzian formulation. The other term was neglected because we assumed that no tension or negative pressure could be sustained at the interface. But when we add in adhesive forces, we see that this term is in fact valid. You'll notice that this term is dependent on the surface energy, since it is these interactions that create the adhesion. For all of these equations, if we set surface energy as 0, as we assume in Hertzian contact, we can recover the original Hertzian equations. Furthermore, a high load will dominate the adhesion terms, and we can recover the Hertzian contact shape. Now let's try a simple JKR example problem. In a typical JKR problem, we know the applied force and the radius of our contact, and we're looking for a pull-off force that we can use to calculate the total gecko adhesion. In this problem, we'll also find the maximum pressure in the contact. We'll use a force of 10 millinewtons and a radius of 250 micrometers, typical values found in synthetic gecko adhesives. Furthermore, we'll assume the contact surface is glass and the CETA is made out of PDMS, so we'll look up the surface energies, Poisson's ratios, and Young's moduli. We may have to determine the interfacial energy experimentally for uncommon material pairings. We can start looking for contact pressure by looking at the Hertzian term. We can already see that we're missing two variables, A and E star. We'll start with E star. To calculate the combined Young's modulus, we plug in our Poisson's ratio and Young's moduli from our two materials to find 480 kilopascals. Now we'll find our contact radius A. You'll notice that this is not our Hertzian contact radius. This is because the presence of adhesion changes the shape of the contact. We have R, E star, and F, but we don't have any delta gamma. So now we have to find the work of adhesion. We can calculate the work of adhesion by adding our two surface energies and subtracting our interfacial energy to find 79 millijoules per meter squared. Now let's plug that into our equation for contact radius. We get a very small value, but note that it is significantly larger than the Hertzian contact radius, which does not incorporate surface energy. Now that we have both our A and our E star, we can calculate our maximum contact pressure. We see that the pressure is maximized in the center, where R equals 0, and that the entire term goes to 1. We can find this maximum pressure. Now we'll calculate the JKR term. We already have all of these values, and we once again see that the second term containing R goes to 0. With this pressure, we combine to find the total pressure, shown here. Finally, we calculate our pull-off force, which is much easier thanks to the special properties of spherical contacts. The pull-off force is negative because it is in the opposite direction of the applied force. You might be confused at how small this number is. 93 micronewtons is not much force considering how well geckos can stick to things. In fact, it is because of the number of CETA, as many as 6.5 million, and not their relative force, that geckos can achieve such impressive adhesion. With this number, we can multiply the pull-off force by the number of CETA to find the total adhesion in our synthetic gecko foot. Of course, not all of the CETA are in contact at once, so this estimate is a little bit high. The JKR model helped us get this far, but let's consider it a little more deeply before we go. Because it's based on the Hertz model, the JKR model does have some weaknesses. For instance, it predicts the stress at the edge of the contact as infinity, which is of course impossible. Additionally, it ignores the adhesive interactions outside of the contact radius, which means that it works best when applied to large, soft spheres. Still, the JKR model can be applied to a wide range of adhesive applications, including particulate contamination analysis, controllable adhesion, and even the deformation of living cells. And there you have it. By looking at the surface forces at the contact interface, we can see how contact shape changes in the presence of adhesion, measure surface energies, and even determine the force with which one object can stick to another.
For more information on adhesion, check out the DMT model, which is used for small rigid spheres and low surface energies. Thanks for watching.